And so today we're gonna continue on what we started the last lecture, so yesterday, meaning that we are gonna talk about how to inherit from classes and what we can do about it. So it's gonna be a lot of this lecture will be really high level. It's gonna be about how to think more abstractly. And then we're going to talk about how to use input-output streams. So for the last homework, you were given a function that would read something from the files, and you didn't have to implement it yourself. But this time, you will need to implement such a function yourself in the homework. So we're going to go through how to use fstream for that. And then we're going to talk a bit about string streams, why they're useful, and in the end, we will kind of find out how to use find package in CMake in order to find external packages that we don't want to build ourselves, that are pre-built for us, that we can just install on our system and use with our code. Again, before I start, as usual, like, are there any questions that you want to discuss before? Like, is there anything that is extremely confusing and you know, like, you've been hitting yourself with the same error for a week and you still don't know how to solve it? That's probably a good time to ask it, and we can just go into example and see how that works. So, any questions before we start? Okay, doesn't seem to be the case. Yeah? Yeah, okay. Okay.
In tests.
Okay.
Because he told me he cannot find the path, and that was clear to me because I referenced to home, user, and so on, and obviously git.
So do you mean you have a problem on your local machine or in the when you uploaded it? So you should never use absolute paths there. You should use relative paths, and relative paths are always relative to the CMake list that you are currently writing. So if you are in a CMake list and you do add subdirectory, if you type, say, source, it's going to be the folder in which this CMake list is, then plus this source in the end, right? So it's always relative. And that's why you build kind of a hierarchy of those CMake lists. So you start with the base one of your project, then you do another add subdirectory, say source, and it means that in source you have to have another CMake list. So why is it done? Like, maybe you now think it's just done for more complexity. It's not. It's done to reduce the scope of your attention. So you want to, like, when you're writing your libraries in your, say, source folder, you don't really want to know about the configurations of your whole project. You want to know how to write your library. So when you open that CMake lists file, that's all you see. So for instance, we can go and so just to illustrate this, come on. Okay. So I will go to some an example that I had in the slides. So everything that you saw in the slides for CMake lists was actually a small project with CMake that I wrote in the repository of the lectures. So I just put parts of it. So all the code that you saw in the lectures is actually working code. It's a project that actually builds. So let's go there, and it's in slides, in listings. Okay, so let's do the project CMake tests. Okay, so now we are in a project which has a CMake lists in it. So this one, right? And the structure of the project is as usual. So it has a CMake lists, it has a source folder with another CMake lists, and it has a tests folder with another CMake lists. From the perspective of CMake, the tests folder and the source folder are exactly the same. They don't have to be source, they don't have to be test, they can be any name that you want. From CMake list perspective, it's just important that they contain a CMake list.txt, and that in the main CMake list.txt they were referenced as add subdirectory. So if we go to the main CMake list.txt file, it looks like this. So again, this is just the example from the slides. So you have exactly this code on the slides. There is a lot of bloat that you really don't care about when you are defining a library. You just want to define your library. You don't care about this whole thing. And that is why you use the add subdirectory. So you want to reduce the knowledge that you have when you're writing your library. Like, you don't want to configure your project at that time. So in this way, you just do the add subdirectory source. And if we go to that one, so if we now open source CMake list.txt, then it looks really, really simple, right? So, and that is what we want. When we write our library, we just want to deal with this. We don't want to deal with all that huge file. We just want to deal with this small file. And it does nothing fancy. It just creates a small library, then it adds an executable, and it links the library to the executable. We've seen that many times, and I hope by this time it's relatively clear what is happening over here. Again, like, if we switch back to the big one, this source folder is going to be relative to the folder where the main CMake list resides. So you should always use relative folders. This way it's shorter, and you also make sure that you have this hierarchical build, like a tree, right? I'm not sure I answered exactly your questions. Like, it's kind of, so I hope it got a bit clearer.
Yeah, I'm not sure why it didn't function. But we'll figure out.
Yeah, I mean, like, we can also just look at, like, I can come back to my desk and look at your code, or look at it from here, so we can find out what went wrong. Any other questions that need to be clarified? Okay, so then I think we're just gonna start. So last lecture we started a bit with inheritance and how the classes can inherit from each other, and we ended up with virtual functions. We're going to use those virtual functions a lot in this lecture. So at first I will give you some information about this whole thing. It's kind of very abstract, and you just kind of have to have it on the slides to return to it whenever you need, and then we're going to dive into examples, and hopefully the examples will show the differences between the different approaches, and how can we use those different approaches for different things that we want to achieve. Right, so there is a word polymorphism, and it's one of the kind of the three big words in the object-oriented programming. And you might have heard about it a bit if you did Java before. So Java is a completely object-oriented language, and that's why it's always caring about the encapsulation, polymorphism, and inheritance. So polymorphism is nothing else, is just something that can take many shapes. And we're going to see why this happens in a bit, but the idea is that if we have a base class and we have a derived class, then we can do something like this. So we can do a reference, or like we can have a const reference, and we can set it to some derived class. So we usually shouldn't do it this way, because this is a temporary object, and anyway, the idea is that we just can't do it syntactically. So probably I should have put like the awful code guy on this slide. I probably will update the slides with that. So the idea is that this is a different class from this one. And the only reason why we can do that is because they are in a hierarchy, they're in a relationship of one is a child of another. So the derived is a child of the base class. And this simple construction allows us to do a lot of things. Like it gives the whole new level to C++ and how the objects can communicate, and you can create like beautiful designs that actually outsource a lot of functionality out of your class. So your class can stay intact while some functionality is outsourced and can be replaced on the go. And we're going to dig into that. So, so there is a couple of use cases which are common. And the idea is that we want to encapsulate some implementation in a class. And okay, let's put it that way. There are like we're going to focus on 3 implementations in this course. So 3 ways of using it. So we can either just provide a like let's say we have a base class and a derived class, and we want them to so they are in the is-a relationship as I told you yesterday. So we can say that derived class is a base class. Then we just want to work with them in a unified manner. We want to have them the same interface, and whenever I say interface, I mean public functions. So they have the same public functions, and we don't really care about which exact class we're working with now. We just want to care that they conform to the same functions. So again, we hide the implementation from ourselves and from the users of our library, and we only expose some interface that people should use. Then sometimes it can be also used to enforce the same interface in otherwise unrelated classes. So let's say we want all the class to have a print function. All the classes in our library, we want to force them to have a print function. We can do that by deriving them from a class that has a public print function, for example. And there is a strategy pattern which we will look in depth, and also there is the pattern that you will need to implement in the homework eventually. And this strategy pattern is needed to outsource. So let's say your class has some complex behavior. For example, your image class, it wants to save this image to disk, right? And you want to be able to switch the way it saves this itself to disk in different manners. So say you want it to be able to store PNG files and to read PNG files, or like PPM files or any others. And this is a relatively complex behavior. To write something to disk or to the hard drive, it takes some effort to code. It's not the most complex functions in the world, but it takes some effort. So you want to be able to, you basically say that there is a different strategy of writing and reading from disk. And I want to be able to replace this strategy on the go without changing any line of code in my image class. And that is why this whole thing is done. So it's very, like, for now, it's very high level, and we are starting to dig into those particular 3 cases. Like, we're going to dig into examples for those 3 cases now. So first of all, it's useful, like the polymorphism can be used to create a class hierarchy. So last time we saw the class rectangle, and a square, say, is a rectangle, and we just want to work with rectangles, and we don't care if some of them are squares. And that is what we use for that. So the square will completely conform to the interface of a rectangle, or even a shape, for example. So it's always about the public interface. It's always about which functions does something have. It's important to distinguish between is-a and has-a relationship. So whenever there is a is-a, so something like square is a shape, or like student is a human, then you can actually inherit one from another. And whenever you cannot say that, so like if the relationship is actually has-a, then you should not inherit, and you should just include like multiple objects so say like a car class should include a bunch of objects of wheel class, right? when you start working with it, like more and more, you will be tempted to do deep hierarchies of classes. So at first you will be scared and you won't want to use it at all, but then when you start using it and it works sometimes, you will find yourself that you want to build like deep hierarchies. So say like, I don't know, a student of this class is a student, and a student is a human, and a human is a monkey, and so on. Like, you know, like you can go like very deep in that, and generally it's not a very good idea. So even though it makes sense logically, from the coding perspective, it hides the implementation details that you care about very deep into hierarchy. So in order, when I'm now looking at the class that, say, implements you, like the students of this particular class, and you inherit from just a generic student. To find something that is hidden in that class, I need to navigate to another file, read it there, and then suddenly I find that it's not even there, it's actually in the human class, so I need to find that human class, and so on. So if you're tempted to do like a deep hierarchy of classes at some point, try not to do it. Usually prefer composition. Composition means include an object of another class in your class. Right, so let's jump into examples. So this is the first one, which is kind of, it's very similar to the one we've seen before. So we started last lecture with the example where we had a rectangle and we had a square, and the square could use the functions from the rectangle. In fact, I think we can also just do it as usual here. Okay, class. So let's say we have a class and it's a rectangle and it has private int width, height. Okay, and we can create it with int width, int height, and let's set those. Okay, so there is a class rectangle, and let's say we also have some getters for them, right? So we want the width getter, and it's going to return width. And the same for height. Okay, and let's say we now want to do a class that is called square, and this square will just take the size. It will call the, so it's the same example as we've seen before, but I feel like it's important to refresh it at this point. Okay, and we don't need any private things over here. Okay, let's make Google style happy. Nice. So now if we have a main function, we can create a rectangle, rect, and it can be, or like not a rectangle, we can do like a square, and the size is 10. And we want to print it. So we want to print it like this, square width, square height. All right, so did I miss something? Ah, yeah, right, of course. Now square doesn't rely on the class rect, so we want to say that square is a child of the rectangle class. Okay? So at this point, this is what we ended our last lecture on. Like, this is the example from that lecture. The idea is that now the square class can use methods from the from the rectangle class. And again, like if you've used Java, you might have already seen that before. Yeah?
So the child-parent relation is made in line 15.
Is what?
Like in line 15, the child-parent relation between square and rect, is that done in line 15 by saying by square public rect, or where does this happen?
Yes, so this says that square is a child of rect. Okay. So whenever it can also, like in C++, it's theoretically possible to inherit from multiple parents. So you can have here rect, circle, whatever else. It's generally not a good idea, so won't be taught in this course. Like, whenever you find yourself that you want to do it, try to avoid that, probably. I think in Java it's not allowed by default. So by default in Java you cannot inherit from multiple parents, and that's the reason, because the C++ people have figured it out that it's not a good idea. Anyway, so this defines that square is now a child of the rectangle. And it kind of makes sense, because you can say that square is a rectangle, right? So it makes sense. Yeah?
And what does explicit say?
Explicit says, it's kind of a, so it's a thing that Google style enforced on me when I started using it a long time ago. The idea is that if you say, if I write here, so let's say I remove the explicit. And now I set this one to 10.2f. What will happen? Yeah, so what will it print? Error? You think error?
Just 10. Oh, it will use 10.
And it prints 10. And the idea is that it's fine if it's 10.2, but what if it's 10.9? It's going to be 10. Like, what if it's 9, 9999999? I don't know. I think that's too many. Oh, that's 9 because it's still like it just drops everything that is after the comma and says, well, you wanted an integer, here's your integer. And to avoid that issue, you want to forbid this implicit conversion of types. And to do that, you use implicit. Implicit suddenly makes this an error. So now, let's remove those. Now it tells us actually the error that we want to see. Oh, wait. No, it still works. Okay, this is weird. Why? Yeah, C++. Okay. I need to study that. Generally, it helps in that case. So what it should forbid the conversion of types when you pass them in the constructor. Now I wonder why this didn't happen. Okay, I will figure it out and we'll write an email on you. Like, sorry for that.
But is that important for the relationship between child and parent?
No, it's not. So explicit is, you can treat it as a syntactic sugar. Like, it's just added there for additional security. Sometimes it helps. In this particular case, it didn't, which is really weird. Maybe I just understood it wrong somehow. Anyway, so kind of when you're using, say, Google style, it will tell you that whenever you have a constructor with a single argument, you should make it explicit. And it doesn't make anything worse if you do it, and it might help you in some particular cases. Again, I will probably elaborate on that more in some email or something, because I got impressed now. Okay. Anyway, so in this particular case, we can also just drop it. It doesn't really matter. It doesn't have any influence on the relationship between the child and the parent. Okay, I hope that's clear, but for now it's a relatively simple case, right? So for now we just had a rectangle and we had a width and height, and we've shown that the square can use the function from there. But let's say we don't want to expose our width and height at this point, but we want to say that we want to print something. So we want to create a print function, and it's probably also a const, and we do something like this. Okay. Now we have the print function. Okay, this should be also just width. And this should be just height. Okay, and now we want to do the square print. Good. So at this point, there is a function print over there. And if we do the square print, it still prints rect 1010. But we don't want to have their word rect. We want the word square there, right? So what we can do is we can just kind of copy this function over and put it here and replace it with square. Yeah, but now the problem is that at this point, okay, we should, again, like now we have the hierarchy, and the private things will not be seen even to the children. So that's when I told you from the start that we have 3 access modifiers. We have the public, the protected, and the private. And I told you that for now we will treat protected and private the same. That is because we didn't have inheritance. Now we do have inheritance, and they're not the same. So private is hidden only for you. So if you are a class and you have a private member, then you will be the only one who will be able to access this private member. Even your children will not be able to see that. If you want your children to see something like that, so you will have to make it protected. And if you make it protected, then your children can access those variables. So now if we run this code, it will tell us it's a square, right? But now we have just 2 different functions, and we don't really know if, so it doesn't make sense that like a rectangle will have the print function and the square will not have the print function. So we want to make sure that we don't kind of copy that. So let's say for that we can introduce a virtual function. So a virtual function, if we just put virtual over here, then so what virtual says is that it says that I have this function, but my children can override this function. Now, in this case, it won't be really useful because we are actually creating a concrete object of square. So whenever we just create a variable of a class, there is no polymorphism in place. Like there is no. So we just create this class over here with kind of copying everything from here inside of here, and that's what we do, right? The interesting thing starts when we create a. So let's do a const. Now so we have a square, and now we want to store this as a. So const rect reference. And we can set it to a square. And now we want to print the rect ref. So if we do it now, we still get the, so if we now build this, we still get the 1010, and it's a square. Because even though it is a constant reference to a rectangle, we know that it should use the function from square. Now, if I remove the virtual from here and run it, you see that the results are rect. Okay, so at this point you might be confused, and it's normal. Let's try to figure out why this whole happens. So, because this is like the cornerstone of everything that we will do in this lecture. The idea is that there is no magic. There is only rules that define C++, right? So what we do here is we create a concrete implementation of square. So we just create an object of square. Whenever we create an object of something, we just create an object of this class, and whenever you have the inheritance, you just kind of copy all the contents of this file into here. And you can override functions. So this function has a different signature than this function because it's in the class square. So the signature of this function is actually square, 4 dots, then print, and the signature of this function is is rect, 4 dots, print, right? So they're different functions. That is clear, right? Okay, good. Then, because they're different functions, you can have the function with the same name here, even though this name is already taken over there, right? How does a compiler decide which function to call? So it just looks at the object that it has, of which type is this object, and tries to call the function with the name that you ask for in the class that has this object, that has this type. So for example, if we call, so if we do the square print, then it will actually call, so it will look, oh, okay, I have an object of type square, right? So if I have an object of type square and somebody wants me to print this object, I should probably use the function from square. So it actually uses the function from square. But then the funny thing happens if I have a constant reference to a rectangle. So I do this polymorphic conversion that the square, you can set it to the const reference of a rectangle. So now, from the compiler perspective, it's a rectangle. Like, it doesn't care that it's actually a square, because now for the compiler, it's a rectangle. So whenever we want to print it, it just looks up the function in the rectangle class, and it finds this print function of the rectangle, and it prints the rectangle. Is that clear? Who is still following? Okay.
Why do we need to write this constant reference?
So the constant reference is, you can also have a reference over there, no problem. Like in this particular case, it will work.
If we encounter this problem, why should we write it like that?
So, like, this is a very simple example to show you how it works. It is not a useful example. Like, you cannot, like, it doesn't do much, right? It just prints stuff. But I always start with a simple example, because if I show you the real example, it will get messy. Like, you have so many things to look at that you will be confused about, should I care about this, should I care about that? At this point, you care about one thing, which function is called, and that's what this example is there for. So it has to show, like, to make you understand which function is called why, because this is very, very, very important for anything that follows after. So this is not a very useful example, but this construction will be used in more difficult cases later on. Okay?
No, I mean, if we want to, that the program shows a square and rectangle separately, so we shouldn't write constant reference, right? Because if you write it like that, then it shows everything as rectangle.
So I'm a bit confused about your question, because you're saying that we shouldn't use the const reference.
Why did we
Why did
we define a square here? I mean the child part. So it shows us that we also have a squares.
Yes, but we want to. So usually we want to work with the most basic class we can. In this case, it's a rectangle. We don't, like, some rectangles will be rectangles, some rectangles will be squares. So we're going to come to that, like, very soon, like very, very soon. Because, like, now it's in one main function, but it can also be a parameter to another function. I don't want to write two functions that will take the rectangle and the square, because then I just copy my code twice. I want one function that just So let's say, let's do it now. Like let's answer your question by an example. So let's say I want my function, and again, it's a very stupid example, but it's very illustrative. And let's say I want to have a function print. Now it's a freestanding function. It's not in any class. It's just a function print. And what it does is it takes a const reference to a rectangle, and all it does, it just calls print on that object. So now what I can do is I can do the print square. Also, let's create a rectangle here, 10, 20. So I can do this without needing to, okay, this is a rect. So in this way, I don't need to write two functions print. I can live with one function print because I know that both of my classes conform to the same interface. They have the print function. So that's all I require from them, and then I can use this print function to do that. And this way, if I wouldn't use the const reference to rect here, I would need to write two of those functions because I would need one for rectangles, one for squares, one for any other shape, right? And this way, I don't need to do it because every shape knows how to print itself. Does that answer your question to some degree?
So now that you have added constant reference, it knows how to show square and rectangle separately?
Now that I added the constant reference, it knows that a square is a rectangle. So that's what it knows. It can convert a square to a rectangle somehow internally. So it can store a reference to a square as a reference of a rectangle. Of course, you can lose some functionality on that, but...
So I mean, when we run this program, what does it show to us when it's a square? A square or rectangle?
So if I run this, you mean? Like, this one will show you a wrong result because we didn't implement it correctly yet. So you kind of like, you intercepted me in the middle of explaining, so that's why it's still in the wrong state. But it will show the correct things in the end. It will show, when we pass a square, it will show us a square. When we pass a rect, it will show us a rect. And that's why we do it. So let me just finish the example, and if you still have this question afterwards, let's keep on discussing on that. All right, so we were talking about why this thing will not really work well, and the idea is that, right, so whenever we have this variable over here, from the compiler perspective, it is a rectangle. It doesn't know if it's a square or anything else. It just gets the constant reference to a rectangle, and from the perspective of the compiler, it is a rectangle, okay? If we don't have any virtual functions in our classes, that is the function that it will call. So if we call this now, we will have twice rect written, right? So now we have rectangle and rectangle. Even though this one should actually be a square, but it's a rectangle because the compiler doesn't know what we want it to do. Like, it just sees a rectangle. There is exactly one function that matches that signature because it looks for a function print in the rectangle class. So it tries to print a rectangle, okay? I hope that is clear for now. And now we're going to fix this situation by adding two words to this program. So the first word is virtual, and the other is override. So now if we run the same program, it will magically know that the first one is a square and the second one is a rectangle. And that is exactly what we wanted to do, because we passed a square, we wanted to print as a square. We passed a rectangle, we want to print it as a rectangle. Okay, now let's dive a bit deeper into why this whole thing happens. Like, why does it, how does it magically know about this now? Whenever we say virtual, we say that we expect this class to be part of a class hierarchy. So there are other classes that depend on this class. So whenever you define a function, whenever you declare a function with word virtual, it means that you expect that this function will appear in the children classes of your class, right? It doesn't have to, but it might. So then in the child class that inherits from a class with a virtual function, it can override this function. Now, override, as again, like we briefly spoke about it yesterday, overriding is, so it's a function with exactly the same signature apart from it being in a different class. So it has exactly the same input parameters, exactly the same modifiers like constant and so on. But the compiler now knows that it needs to, so not the compiler actually, it's happening now not by the sorry. When you run your program, you know which function to call, not at the compile time, not while you compile the code, but at the runtime. That is a huge difference to function overloading, which happens at compile time. Now, what happens here? So whenever you say virtual, your class allocates a table. And this table basically just maps from the name of your class to a function. So let's say I have function print, and I just created this class for now. It now has a table which contains one entry, and this entry is function print, or like my class rect, and then this function print over here. Then when I create a child of this class square, and I override this function, it adds a new entry to this virtual table of the rectangle class. Now it has two entries. There is one entry rect to print in rect, and the other is square to print in square. And what happens when we call print, so whenever you call a virtual function, at the runtime, the processor will look in this table, and judging by the kind of the polymorphic type of your variable, it will find the correct function to show to you. So this way, it will know that you actually, even though you have a const reference to a rectangle, you actually had a variable of square. And this is why it will eventually, it will look here and it will find that this function matches better because you actually have a variable of a square. And this is basically how it works. So whenever you, like, we're going to see this a lot. So there's going to be a lot of virtual functions. And whenever you have a virtual function, you want to override this function in the child. Yeah?
Why do you need the override? I mean, if the virtual says, okay, there's a table and those are all the same functions, or not the same functions, but...
Yeah, so usually the compiler will still do the right thing if you don't do override. So it's still figured out that it's a square and it's a rect. And override was added as the new keyword in C++ 11. And I strongly suggest to use it because of, I will come to it in a sec. So if you have override here, and let's say you forgot const, for example, right? Which is a very typical error. You do it all the time. If you forgot const, your signature of a function is different. And now if you save this, this file, you will suddenly have an error that your non-virtual member function marked override has virtual, non-virtual member function marked override hides virtual member function, right? What does it mean? It means that you've defined a function with the same name without const, and this function will hide that function. So what you wanted to do, you wanted to override this one, but you actually overloaded it. You have overloaded it with not having const. And this is a mistake. You probably didn't want to do that. You wanted to actually override it. And this is the only way, so using the word override is the only way to keep yourself safe from those errors. Okay? So always use override. You can also use, like in the old days, so don't do it this way, but in the old days before C++ 11, you would do something like this usually. You would declare this function as virtual2, and then this would show that you are actually trying to override. But if you forgot const over here, well, bad luck, you just created a new function, and they will not be in the polymorphic agreement, so you will not be able to, at the runtime, you will not be able to find the correct function in this case. So if I run this, you will get rect and rect, right? Which is a mistake. And it's a very subtle mistake. It's a very easy one to make. You can easily do it. And that's why generally people, like nowadays, it's a good idea to always use override, because then it actually shows you an error when there is an error. Yeah?
Did I get it right? You're talking about using override in the children function?
Yes. So you create a virtual function in the base class, and you override it in children. That's the general rule of thumb. Theoretically, you can also, like if you have a multi-layer hierarchy of classes, you can override every single, so you can have multiple overrides. So if I have another shape that is a child of square, I can still use override print there, and it will still work. So override is just a syntactic sugar of also declaring it virtual. So it's not really important. So you can use it very deep into hierarchy, but we will only use it on one level in this course. And I strongly urge you, whenever you want to go like deeper than like one level of inheritance, think about it. Maybe you're thinking about the problem in the wrong way. Maybe you should rethink the way you're addressing it at all.
But I could have public class shapes.
Yes.
And class is square and rectangle, and they can both override.
Yes. It is possible, and this way you will have two overrides. So that's probably still valid, but whenever you have it, think maybe you should really treat like then square as a different shape, because whenever you have deep hierarchy, the problems that start with it are, so you will run into problems at some point, and just from experience of a lot of people, it's not a good idea. It's better to copy over some code. It's a learning process. There is some trade-off, and the problem is that it's the only person who will know what is correct and what is wrong is you in the end. So you will need to try one thing, try another thing, find out, oh, okay, I've done this, and it did exactly what I expected. Or I've done this hierarchy, and now I don't know where things are, and I'm confused, and when I want to change something, I need to change everything, and this is probably a mistake, right? And then you remember it, and the next time you don't do it. And this is how you learn those things. But a rule of thumb is when you find yourself doing a deep hierarchy, try to avoid that, because a lot of people have burned themselves with that, and kind of try to use their experience for your own. Okay.
Every time that you have parent and child interfaces, you have two classes, you have to use that constant reference, right?
If you want them to kind of be what we will call here polymorphic, so it means that you can represent one as another, that only happens through references and through pointers. But we will come to pointers in 1 or 2 lectures, and then everything will, then we will know everything. But for now, it's going to be references for us. So for this particular lecture and for this homework, it's going to be references. If you don't do references, it won't work. So if I do a copy over here, let's say I don't do the reference, I actually do the copy. Then I run it and nothing can save me. It's going to be 2 rectangles because now it's not, it forgot that it was created from a square. Like it was just copied there because you can still copy them somehow, but now it's just a rectangle. So it will work only with references. It can be const references, it can be simple references. We will probably use const references in the course, like in this particular lecture and the homework, but it works only with references, well, and pointers too, but for now references. Okay. Good. So I hope that kind of made it a bit clear of what it does and why can it be useful. Let's probably return back to the slides. So this is exactly the example that we've just seen. So this is our print function. It prints a square, prints a rectangle, and they're defined. So it's exactly the same as we had before. Again, it's there on the slides for you to just copy over, try things out, and so on. Okay, that was the typical inheritance with overriding some functions, right? There are more advanced methods, ways of using the polymorphism for prototyping high-level interfaces of your code. If you have, so if you say want all your classes to be printable, like all of your classes in your code base, you can actually force them to be. Like you can have a convention that every class that you define in your system will have to be a child of some interface, and this interface will say have a function print, right? So this way, every class will be forced to implement or to override this print function. Generally, interfaces are a nice thing because they allow you thinking in what functionality on a high level do you expect from a class. So the good part about interfaces, that was I think the last slide on the last lecture, interface is a function that has only pure virtual functions. So pure virtual functions, let's refresh that. Probably that was a bit too fast yesterday. So let's say this is not the best example from the abstract perspective, but just to showcase what a virtual function is. So in case we want to have, or should we do the proper example? Let's think. Let's do the proper example. So let's create another class and let's name it printable. The names are kind of arbitrary. So the interface, usually you want the name of the interface to tell what you expect it to do. And let's say printable, so we want it virtual, of course, virtual void print const. And then the difference is that we say it's equals to 0. That means it's a pure virtual function. It means that it has no implementation in this class. It's just the declaration of this virtual function. Now, what it does is if we now do the public inheritance of the printable over here, we are forced to implement that function. So let's say I removed this one, and if I try to build it, I will get an error. And the typical error that you will see if you forget to override a pure virtual function is something like this. Cannot declare variable rect to be of abstract type rect. Abstract type is any type that has at least one pure virtual function without implementation. Okay? So in this case, what will happen? Like it has public inheritance from printable, so it will copy this function over here. And then the issue is that we don't ever implement it, so now this class also has a pure virtual function because it has copied it from the printable class. And that's why we cannot create an object of this class, because if we try to create an object of this class, it tries to instantiate a function which it has no implementation for. And then you will have this error. Is that clear? Or any questions to that? Not really. No. What is not clear? Fire away. Okay. Okay. The core things that you need to remember is if you create a virtual function and you equal it to 0, it means it's non-existent. Like the implementation doesn't exist. That is clear, right? You cannot create an object of a class where a function doesn't have an implementation. Okay? So whenever you try to do that, the compiler, so generally if you would forget this equals 0, it will mean that you just declared the function and it was never implemented. And when you would try to use it, it would be probably a mistake. But you don't want it to be that late in your code. You want it to be at compile time. You want the compiler to help you. And for that, you set it to 0 over there. And this way, whenever you try to create an object of a class that has a function like this without any implementation, the compiler will tell you you're wrong. The compiler will give you this error over here. And this is exactly what you want, because the compiler kind of has your back. Like, it will tell you, no, you wanted to do this, but you made a mistake, and you are now trying to do something different. So that's why this needs to be done. So I hope we are now on the same page why this has no implementation and why the compiler tells us that it's wrong, right? So this is relatively clear, right?
But when do we use this?
We are going to come to that in a sec. But then we can also override. So now when I add back this function, we have, so now we don't need to have it virtual. We can have it const override, because now it just overrides the function from the interface over there. And if we build this thing, we still get our square and rectangle, so they still work. Okay, so I hope that kind of showcased what is an interface. So this is a very simple interface. An interface is any class that has only pure virtual functions and no data members. It's a convention. There is no such word interface in C++ as, say, in Java. In Java, it's a separate word. But in C++, anything that doesn't have data members and only has pure virtual functions is by convention called interface. So when you talk to other people and you say, I've created an interface, they expect this. Okay? Good. So, yeah.
So you make those virtual functions, like you pack them in a class to use them in the code without having to make an object of a class in order to use the functions of those classes.
Yes. The idea is that you want to be able to construct as many classes as you want at any time that will conform to this interface, and you want to replace those classes when you want to. But there will be some class that will use this interface inside of it, like a const reference to this interface, because you can have a const reference to this interface, or like a pointer, which we will talk about later. But for now, it's going to be const references for us. So it will have a const reference to printable, and it will just call printable print, right? And it doesn't care who implements it. And you can actually replace who implements it at any point of time that you want. So when you create an object, you can just pass a different interface to it, and it will behave differently. So it's much more, you're much more relaxed on what you include in your class. So your class doesn't have to know about it. But there will be an example about that. Yeah. Yes.
Then you repeat what in line 29, what does it mean? In what context?
Here?
Yeah.
Okay, so it's just a function. It's a freestanding function out there, and it takes a const reference to a rectangle, right? So what happens is because they are polymorphic, these types, the rectangle and so on. Like now we can even do better. Now we can do a printable. So now they're all printable because the rectangle relies on the rectangle relies on printable, the square relies on rectangle, so square relies on printable too. That's kind of answering your question about the deep hierarchies. It gets complicated. You get lost in it. That's why you generally would, you can also just put printable instead of rect here, for example. But anyway, going back to your question. So now it can be just a printable, and when you pass a variable into this function, it will be converted to this reference. It will still be a reference to the same, like a reference is just kind of kind of, it tells you where to look for that variable, right? So we have created a real variable, say rectangle over here, right? It lies somewhere in the memory. Whenever we do a const reference to it, it just tells us, yeah, you need your variable, it's over there. It lies right there, okay? So that's when we use the const reference. It will still point to the variable of type rectangle. And this one will still be a variable of type square. But the const reference, it's hard to explain in words, but the idea is that you can use the most abstract reference you want to for all the polymorphic types, for all the descendants of this type. And it will still work by the construction of C++. And the only place where it knows it's actually a square or a rectangle is when you call virtual functions of it. If you don't call virtual functions of it, it will behave just as the object of whatever reference you have. It's kind of...
Can you run it now?
Yes.
Then what was that constant printable reference?
It makes now no difference because they are now all in one hierarchy of classes. Because now they're all printable. Now a square is a printable. You can still say is a, right? A square is a printable because it is a rectangle, which is a printable. Okay? So there are like two is a. Yeah?
So this function just prints the things that are printable.
Yes.
So it worked now.
Yes, it does. Like it works for the last 15 minutes, I think. So, yeah. I mean, it's a dumb example. Like it's example with one function and it's called printable. But in the homework, you will have to have an interface that will be responsible for writing and reading to and from files. And I assume, like, this time I try to give a bit more information in the homework and provide more implementations already. So hopefully you will be able to also look at how other things are implemented. And if you implement it, like, of course you will make a lot of mistakes while implementing it, and it's totally fine. And you shouldn't be afraid of that. But when you figure it out, you hopefully will understand why it is useful and how easy it is now to replace just, like if you have your image class, if you pass a strategy to read like from PNG files, you will be able to read from PNG files magically. And if you pass a strategy to read from PPM files or write to them, you will magically be able to do that without changing any line in your image class. So that's kind of the real use case for those things. And this is a very simplistic one.
So every class that has no implementation is an interface?
Every class that has the virtual functions that have no implementation, that are equal 0. So it's not just not implementation, it's explicitly saying that they have no implementation.
When did we get an error for that? Because you said...
I get an error for that if in the rectangle class there will be no function like this. So if I remove this function print, right? Now what happens is, so again, public inheritance is not complicated. It just copies all the contents of the base class, in this particular case it's printable, into the child class. In this particular case it's rect. So it will just copy all this into here. So it will take this function, copy it over here, and it will still be a pure virtual function. It will not do anything else to it, right? So that's what it does. Whenever you see the public something, it just prints over the things. Maybe apart from the private members. The private members are ignored, but everything else gets copied. In this case, if I now try to instantiate, so the issue, why do I get an error? I get an error because of this line over here, because of this line over here. Because I actually try to now create an object of type rect, but my type rect is now an abstract class. It doesn't have an implementation for the print function. It not only doesn't have an implementation for print function, it says that I explicitly forbid implementation for this function in this class. But I need this function because I want to create the object of it, and then I fail. Okay? Good. Yes.
We need this line because of the polymorphism.
Come again?
The line 29.
Line.
Because of the polymorphism.
Yes. So it works because of this polymorphism, because we are calling a function which is a virtual function, and because it's a virtual function, at the runtime it will look up the function that matches our expectations best. So it will actually look at the object that our reference points to and will match the name of that class to the function that we want to use in our virtual table. Okay? Or was it too fast? Okay. I mean, it's kind of hard to understand what you don't understand, because, you know, like, when you are too long in that, it's hard to get what is not intuitive and what is intuitive. So what you need to remember is that every class that has a virtual function has a virtual table. Whenever you use a const reference or a reference to this class and call a virtual function, it will be looked up in the virtual table at the runtime, and you can override virtual functions. Okay? This is kind of the take-home message from here. And then just, again, go to examples, like copy them from the slides and try them out. Like, do simple, really simple things. Try to get a grasp of why is it there, what is an error, what is not. If you don't understand an error, ask. Okay? Good. Again, this is the same example as we just did in the lecture. So now we have this printable thing, and it's all just the same. Good. The only thing that is here different is that we use structs instead of classes. It's not very important. I just used it for saving space. If you want to read more about this, there was a link last lecture, and it will be in this lecture too. I will not stop on this right now. But structs are just classes with everything public, so you can still use those. But you shouldn't, because you should use classes. Okay, now the strategy pattern. This is the one that you will be implementing in the homework eventually. The idea is that it depends on an interface. So you basically define a bunch of classes that conform to some strategy interface, which is just an interface of whatever you want to do. And you hold a const reference to this interface in your class, in the one you're actually implementing. So let's just do a small example over here. Let's just go over it here. So for example, let's say I have an interface strategy, right? Again, I will use structs here, but it's just to avoid always writing public everywhere. And it's still like, I will still use the print example. So it uses this print function, and it says that it's a pure virtual function print. So that's what I will be using. And then I have two implementations of this print strategy. So I have strategy A and strategy B. They both rely on the strategy interface. I hope that's kind of clear. And they both override the print functions to print A and B respectively, right? That's what they are doing. So they are different classes that just define this function. Again, it can be as many functions here as we want to. It can be 2, 10, 20, whatever. It's still an interface, and all of those have to be overridden in the children of an interface. So a strategy A will override this function to print A. The strategy B will override this function to print B. Okay, that's hopefully clear. Until this point, until this line of the slide, it's still the same as we saw before with an interface. We just defined an interface, and we have overridden this interface in two instances. Okay? From this point on, it becomes a strategy pattern. So the strategy, it's one of the patterns of designing your software. It's a very powerful one. A lot of people use it. And the idea is that we have some structure. It's not important what it is at this point. And we want to store a const reference of a strategy in our structure. Why would we want to do that? Well, that's because we want to have, say, an instance of of our structure that has one behavior and then another instance of it that has another behavior, and we don't want to change any code in our this class myStruct or the structure myStruct. How does it look like? It looks like this. So this will print A, this will print B. And the idea is that, as you can see, that we never change anything in this class over here. It doesn't know which print implementation it will use. It's defined by the variable that we set to it. Okay? So this strategy is set from this variable over here that is passed over here. Okay? Who is on the same page with me? Who got the idea? Okay. I hope that in the homework it will make more sense why this is useful. So the only thing that you have to be careful with const references, again, like I didn't want to introduce pointers here, but generally it's all used with pointers, but it works just the same with references. The thing that you have to be cautious about with references is not to bind them to temporary objects. So don't really do it like this, and in the code that you will be given as the homework, you will have some examples that will not do it that way. The idea is that we create a temporary object here, and because of the internals of the C++ implementation, the C++ implementation, when you pass a const reference to something, it extends its the life of that object until this const reference is gone. So what we do here is we pass a local object from this stack, from this scope over here, into this function, and then we try to store this const reference here. So the question is, will it still be alive when we use it? Will it not be alive when we use it? That's an issue. So try to always create a local variable here and pass this local variable over here. That's the way you should generally do it. I just did it here, not that way, to save some space. All right. So I hope the strategy idea is clear, and that's, I think, yeah. So the other, like the last message is, it's not probably for now, it's not really important for this homework or for this course even much. Maybe when you're going into your project and you really fancy to implement some complicated pattern like of many structures and so on, like you might feel you want to do it that way, try to not overuse it. So try to only use it when you cannot solve your problem by any other mean. If you feel like, oh, okay, now if I want to change this, what will I need to do? And you understand that, oh, I need to actually copy this whole class over again, and it's going to be like 200 lines of copying. I don't want to do that. Then you should probably think about using those patterns. Otherwise, if it's a simple class that has one implementation and does one thing and should never change, then just don't make it a virtual function. Just make it a simple class, simple function that does one thing. So again, it comes with experience, I guess, and there is no good design, there is no bad design, there is the one that works for you and the one that doesn't. And when design doesn't work for you, it means that if you suddenly need to change something and you feel like it becomes really, really, really painful to change something, it means that your design was wrong from the start. And then you have to redesign your things, and this is painful. Finding a good design is a very complex topic. Everybody searches for it. Like I'm still searching for, like every time I start something, it's still a guess. Like you get better in it, but you still fail sometimes. Good. So now back from this abstract world into the real world, kind of back to the simple usage of some functions to do some simple stuff without actually thinking about those classes and how they relate and so on. So let's go back to doing something more simple. And we're going to talk about streams again. So you know already the streams, the IO streams, so the one that map to std out and std err. We're going to talk about the F stream now. So it's the stream that writes and reads to and from files. The idea is that you have to include this F stream, and when you include this F stream, you can use the if stream to read something from a file, you can use offstream to write something to a file, and generally you use one of these two, but you can also have one that does anything of that. So it can read and write, but in my career I have never used this one. It's just there for information. Usually use these ones. There are many...
This is a test for our previous homework, right?
This is actually what you, like in the previous homework, I've given you the implementation for that. Like it is provided in a library. I have used those and implemented the reading and writing into the PGM files for you. This time you will have to do it yourself. I just didn't want to push it all into one homework. It was already, as I feel like, kind of on a borderline too much, and kind of, it's hard to estimate before-wise. But I still, like, I didn't want to push it all into one homework. And that's why you were just using a library for that. Now you will not use that library, you will actually implement such a function yourself. It's not that hard. Like, it's just as using cout, cr, and so on, or cin. It has exactly the same syntax. But first, let's talk very shortly about the modes that you can open it with. There is really a lot of them, and generally, like, it's not really a lot, but these are all of them. And we will not read or write binary files for now. We will just read the text files and write text files. Binary files are a bit different. They're handled in a different way. Generally, like in this course, like for now you will not really need those. It's just this slide is there for your information to kind of go back to it if you want to, if you need it at some point, but you will not need it for the homework because the default parameters for this mode are fine for us. Okay, so let me actually prove to you that it's actually not hard, right? So when we have a, we can use the f-streams when the file contains organized data, when it has exactly the same, say, number of columns in a file. So let's say we have a file that has like an integer, then a double, a string, and another double, and we want to read them with the f-streams. And again, it's important to understand that this is easy to read because it's always the same. It's always an integer, a double. No, wait. This is wrong. Sorry. Have to change the slide. So let's assume there is only one over here. So no word. The idea is that it has to be always the same style. It has to be integer, double, then string, then double. And in this case, for example, it's going to be an integer, a double, a string, and then nothing. And then you break the whole thing. And so you can read kind of these files. So ignore the first line. So these lines, but you cannot read a file like this. Why? That's because it looks kind of like this. And there is a lot of boilerplate from like what we include and so on. Ignore that. The interesting part starts here. So we want to read a file, and this file is testcolumns.txt, for example. And you can use this mode, but you can also ignore it. By default, it works well. What you do is you just use the same operator that we've been using before for cin. So whenever you wanted, like in the first homework, you implemented this game where you needed to pass some parameter into it, and it would read it. That's exactly what you were using there. But now you're not reading from the terminal where the user has to input something, but you're reading it from a file. And that's the whole difference. And every time you use this, it's just an operator in some class. And this operator in some class returns a value. And this value can be transferred to a Boolean. So whenever you actually can read something, it will return you a true. If you cannot read something, it will not read it, and it will return you a false. So that's it. And then you can also put this whole thing in a while, and you want to read an integer, a double, a string, and another double. And you want to do that until you can, right? So to read the whole file. So it's very simple. And then you just output them all. I will not run it, I think, because it's you just like create a file create a file just like this one and run it with this code, you will see that it outputs this file in the console for you. Okay? I hope that is clear. So there is really no magic here. It's just remember that this operator returns the kind of a Boolean if it succeeded or not. And you can chain them, as you can see here. You don't have to. You can use it once. You can use it twice. It depends on how many variables you read. And every time you read another variable, it skips all the white space until it. So kind of it reads like an integer, a double, string, and a double, and it doesn't matter how many white spaces between them there are. It will skip all the white spaces or the new line characters and so on. It will just read them. Kind of the first thing that is not a white space will be read.
But the order of it is important.
It is important. The order has to be exactly the same because this is in your code, this will not change, right? So what you expect an integer, a double, a string, and a double. And this is the way your data should be structured. Another way to read the files is to use getLine. So let's say if you have a file that looks something like this, which is not structured, it's, well, it is structured, but in a very different way, right? So you cannot read it in that way. You can also read it in using the function getLine. And the idea is that you still create an ifstream object input. You give it a file that you actually want to read. You give it that it's going to be an in. Again, this can be ignored. I thought I removed it from everywhere in the examples, but I didn't. And then you can use this getLine function. Again, all of those functions are in std namespace. It's just that we're using namespace std here for saving space, but they're all in std namespace. What you can do is you can do getLine. getLine still returns you a Boolean if it succeeded or not. And what it does, it takes an input, so this input, and it populates this line by it. So whenever you have to already have a variable of type, say, string, and it has to be a line. Yeah, so when you do this, your line, like it reads one line from your file until the next line, and that's it. And it puts it into a string. No magic. Then, like, I will probably not go deep into that. Like, this is just to show that we can search something in the strings and so on. Again, this is not important really for this particular course, but it's just something for you to maybe look at if you have the time and just play around. Good. So what about writing? Like, reading is, we kind of understood how that works. Writing is even simpler because there is no, like, we don't need any get lines there. We can just write whatever we want into files, and we write it exactly as we would with the typical with the CR or cout, for example. So we create an offstream object out file, and we give it a file name. Some file name, it doesn't matter which one. Then we can check if it's open. That's a good idea to do it. If it's not open, we can return exit failure or any integer, or like it's actually any integer from 1 to say 255. It's going to be an error because we want to say that our program has failed. And then we just write to it just as we would to cout or cr, right? So it's exactly the same. The syntax is exactly the same. You still use end line to make a new line. Yeah, there is really not much to it. I don't think that's very much different from cout and cr, and I don't think you will have many problems with that. There is one more type of streams that we didn't cover, and I think now that we've talked about the other ones, we should also cover this one, kind of as a bunch of them together. It's called a string stream. And string stream is just another type of streams. Like, they're all called streams because they conform to the same interface of using the same operators to be read and write, right? So we've seen the CR, Cout, Cin, F stream, and so on. Now it's going to be a string stream. And why would you want to do that? Is if you want to create a string from something, say you have a bunch of integers, doubles, and so on, and you want to create a string from them, like a string variable. You can use string streams for that. Or if you want to break up a string, so if you have a string that contains like two doubles and a string in it, like, and it's one string that you have, and you want to actually split it into three, the problem with C++ is that it doesn't really offer really nice functionality for working with strings as, say, Java or literally any other language on the planet. I don't know why that is still the case, but we have to deal with not having functions like split or something like that on strings. And to work with those, we will use string streams. An example of this can be something like this. So you can create a string stream, like an empty string stream like this. Then you can write to it like this. I will not probably cover now these functions, just try them out, see what they do. I think it's much better than I explain it now. And you can get a string from a string stream file. So once we put things into the string stream, we can get a string out. And this is just a string. We can also clear a string stream by doing this. So we can set a string to it. And that's basically it. Right. You can also initialize it from, okay, this might be not the best variable name, but the idea is that this is just a string. So you initialize a string stream with some string, and then this string stream will have that. Again, I think it's much easier if you just try to run it and see what it does than me talking about it, because it's a lot of word string in one sentence, and even I get bored of that. Right. So the last thing that we want to cover today is CMake. Like, it's one last bit that is missing from CMake for us. This is the find pass, find library, and find package. So we'll start with find pass and find library. Again, as you got the email yesterday about the replacement in the CMake things, the idea was that usually you use these functions. The ones that I used in the previous lectures, that was a mistake. So I shouldn't have used that. It does a lot of things that I was not aware of, and that's why a lot of people got problems with that. So these things are solid. Like, they're used all the time. They're well-defined. They have a well-defined behavior, and we're going to be using them a lot in the course too. They're used for finding some external libraries or for using in external libraries. So if we want to use a library, as usually we want a header file or a couple of header files, and we want a binary file for this library, right? To find the header files, we use the find path, and to find the library, we use the find library functions of CMake, right? So what it does, like, if you want to search for headers, you use find paths. This will be the variable where all those paths that are found will be stored. So it's going to be populated by a list of all those found paths. It's just a variable in CMake. Then this is the pattern that you are searching for. So let's say you're searching for some file, and it's going to be an include folder. So you want to find all the folders that contain this file with this path to it. So let's say there is a folder blah include some file. This will be populated by blah. Okay? And you also give some paths here, like other paths that you might want to find. Good. And yeah. So. And then you can use this thing in include directories just like this by using this as a variable. And the same goes for libraries. The idea of using this function is because you don't want to write your own, like, that you're searching for SO or for .a or for something. You just want to say, I search for library named like this. and it will search for everything that ends with SO or .a and so on. So what you do is you give a name of your library. This is what will be populated. This is again the variable that will be returned for you. You give some names that you want to find. So say in our case it was IO tools, right? So we had that example before. So you would type IO tools here, and then you give pass where to search for it. So you tell it to look here, there, I expect it to be there, and so on. And when you've done it, you have to link it to some target of yours, because you were finding it to link against some target. So say it's going to be your main function or your library or whatever else, and then you just link it like this. So you use this variable that was populated over here to do it. This whole thing you usually don't have to write yourself. Usually you use find package. Find package calls multiple find paths and calls multiple find libraries. It's doing it on its own, kind of in a separate file. Whenever you use find package and you give a package here, it can be any package name. CMake will, it's no magic again. CMake will just search for a file that is called find, and then it will just put this name over here, so it's exactly the same as there, and it has to end with .cmake. And it searches it in a path that is defined by this variable in CMake. You can always print it out with a message if you want to see what it is within your CMake lists, but that's what it's going to do. So when it finds this file, it will just go through this file. Like it's just a scripting language. It will find this file, go from line 1 to line whatever end, and will do whatever that file does. And that file populates a lot of variables, so like your libraries and so on. The good part about it is that it's predefined for a lot of libraries. For most of the libraries that you want to use, there is already a find package whenever you sudo apt install them. So if I install, say, a PNG library to read PNG files, then it will automatically install a find package like this find png.cmake, and then I will be able to use find package, this library, and will just be able to use the variables that it populated. So I will not need to write any code of my own to search for any libraries, which is very useful, and you generally want that because you want to be lazy and not do it instead. So the way it looks like, kind of like this, is if you have some project in CMake, and so we can set our own CMake module path if we want to. Generally, you don't need to do that, but you can do that. Then you just want to find some package. And the typical names that the find package defines for libraries and include directories are these. So you have exactly the name of your package, then underscore include dirs, or exactly the name of your package underscore libraries. And this will contain all the libraries defined by this package, and this will contain all the include directories defined by this package. This is not true for all the packages that you might want to find. Unfortunately, it annoys me as hell, but sometimes it's not like that. But you can always just find something file, look into it, see what it defines. It's just a CMake file. Right, so again, to show you that it's not magic, so here we wanted to find package some package. So what it does, it searches for this file over here. It goes to CMake modules, find some package.cmake. And it's just another CMake file. It's just a small part of it, right? So what it does, it finds some paths of some include, and it has to be some package include dirs, and it finds a library, which will be some package libraries, and it searches for some library name and folder of where to search. Okay, so it's just like you will not need to write those files. It's just for you to understand that there is no magic, and when it doesn't do what you want it to do, you can always look inside and understand what it does. Oh, okay. I think we're done here for today. Yeah, so the next homework will be about, it's still going to be an image class, but now it's going to be a color image. You can use a lot of code from your old class, and we will drop the compute histogram part from it completely. You will get the PNG strategy, so you will have to implement a strategy for saving and storing, for saving and reading the files. And you will have to implement your own reading from PPM files, which is exactly as PGM files as before, but now they're color images. The PNG strategy will be provided to you, so you will be able to see it. But you will still need to make it useful with CMake, so you have to do the find package PNG and so on. But a lot of things, I tried to, the homework, this homework will have a lot more text on the exercise sheet. Don't be afraid, it doesn't mean more work. It means more explanations of what you need to do. Okay, so that's hopefully it. And the deadline for the next homework is not Wednesday, it's going to be Thursday because there is one, I think, weekend. So next Tuesday is going to be a weekend, I guess. So you get one more day for just relaxing. And again, if something doesn't work, yeah, let's talk about it. Thank you.